In this video, we're solving an energy conservation problem involving friction. In other words, we have a non-conservative force messing with the total energy budget. So the setup for the problem is that we're given a spring of constant 85 newtons per meter. That's been compressed by 40 centimeters relative to the equilibrium position. And that equilibrium position is marked with that vertical dashed line. And there's a block of mass 0.65 kilograms pressed against this spring. And we're going to release the system from rest, but as the block is sliding, it feels a kinetic friction coefficient of 0.18. Now in the first part of the problem, we're going to find the speed of this block when it comes back through the equilibrium position, and then we're going to find out the total sliding distance after the block passes through that equilibrium point. So to answer part A, the speed of the mass when it returns to the equilibrium position, we're going to start from the beginning here and say that E initial plus any work done by non-conservative forces must be equal to E final. So just the basic statement of conservation of energy in the presence of a non-conservative force. So in the initial state, that's all spring potential energy. And of course, the work done by the non-conservative force, that's the work done by friction. And then in the final state, that's the kinetic energy of the block, and all of the energy is gone from the spring. So we need to set ourselves up to compute the work done by friction here. So we should probably have a complete force diagram on the block, allowing us to compute the friction force. And there are no surprises here. We have gravity pulling straight down with a magnitude of mg. We have a normal force that's equal to mg because there are no other vertical forces tampering with the system. And then pointing to the left here as the block slides to the right, we have our kinetic friction force, which can be calculated as mu k times the normal force. So subbing into our energy conservation equation, we have an initial energy of 1/2 kx initial squared. All the energy is stored in the spring at that moment. Then we have the work done by friction. Well, that points exactly opposite the direction of motion. So this gets a minus sign, and it's force times displacement. So the force is our friction force, mu k times the normal force, but the normal force is mg. And the distance that force acts through is also equal to x initial, in other words, 40 centimeters. Then in our final state, all of our energy is kinetic, so it's going to be 1/2 mv squared. So we'll just go ahead and plug in numbers at this point, and I have 1/2 times k, that was 85, times x initial squared, that's 0.4 squared, minus mu k, that was 0.18, times the mass, 0.65, g, we're going to use 9.8 for that. And again, that force acted through a displacement of 0.4 or 40 centimeters. And this is going to be equal to 1/2 times the mass, 0.65 again, times the unknown final speed squared. Now you can handle this all at once in your calculator by just smashing all those numbers on the left side of the equation, and then multiplying by 2, dividing by 0.65, and square rooting the result. And when I run the numbers on this to 3 significant digits, I get 4.42 meters per second. All right, next we're asked to compute the distance the mass slides beyond the equilibrium position. So we're going to use the same basic concept of energy conservation for this. And we have a choice here. We can start all the way back at the initial state where the block was compressed against the spring, and then we'll have to compute the work done by friction over the 40 centimeters there, plus the additional x that it takes to slide to a stop. Or we can start at our intermediate position where we're at the equilibrium point and we have all of our energy in the kinetic system. When I solved the problem, I just went ahead and started from the intermediate state, but you should be aware that that can cause compounding rounding errors that might make your answer a little less precise. So again, we start with the basic statement of energy conservation in the presence of a non-conservative force. E initial plus any work done by non-conservative forces is equal to E final. And in this case, all the initial energy is kinetic. Again, we're starting from the equilibrium position where the spring is relaxed and the block is moving at 4.42 meters per second. So we have 1/2 mv squared. And then I need to write down the work done by friction as we go through this additional distance of x. Well, it's very similar to last time. I have the force of friction mu k mg, and then I have to multiply by this displacement of x. So that's the unknown that we're trying to solve for this time. Now in my final state, I have a block sitting at rest in a relaxed spring. The total energy is 0. So we could solve for x symbolically, but since we've already sort of done things numerically in the first part, we'll go ahead and just plug our numbers in. But first I want to point out that the mass does cancel out of this equation. So we plug numbers in, and on the left-hand side, I have 1/2 v squared, so 1/2 4.42 squared, minus mu k, that's 0.18, times g, that's 9.8, times this unknown x, and that's all equal to 0. So again, we can do it all at once in our calculator. We'll just imagine adding that negative term to both sides, and then we compute 1/2 times 4.42 squared, and divide by 0.18 times 9.8. And to 3 significant digits, this gives us a sliding distance past the equilibrium point of 5.54 meters. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.